5 hours of fireworks. And some people spend a lot of money on fireworks. Sparkler? Yeah. Okay, so I know it's been a while since we've been here. Let's just discuss quickly what it is that we had stopped with. We had discussed this idea of taking two functions and looking at the region bounded by the two functions and rotating it around the x-axis. And to do that, we looked at an infinitesimal sliver and then found some sort of formula for the volume of that sliver rotated around. And we came up with this thing called a washer. And then we came up with a general formula for it right here. So just remember that with this formula, you square each function before you subtract them. You don't subtract them, then square. It's totally different. And I believe that's where we stopped, right? So I think we need to do an example of this, and then we'll keep moving on. Oh, what I was going to show you. Remember I told you I was going to show you something cool with this? So let me do that one first. Okay, so if you go and you look up on your formula sheet, if you're given a sphere with radius r, what is the volume of a sphere of radius r? 4/3, y'all excuse me, 4/3 pi r cubed. So that's the formula. If you know the radius of a sphere, that's its volume. But this section is about trying to find volumes by rotating things around the x-axis, right? So perhaps we could come up with this formula on our own. In other words, where did this formula come from, right? So let's talk about this. How could we use what we just talked about, well, last week, to somehow construct that solid? What could you do? What's that? Okay, so yes and no. Yes, we can take the object that looks like this, right? Just that. Take that region, rotate that around the x-axis, and that would become a ball, wouldn't it? Yes? Now, but the only thing was not a parabola. We wouldn't want this to be a parabola. We would actually want that to be half of a circle, right? That's what you would need. It's for that to be half of a circle. Also, what about us doing this instead? I mean, this is going to work, but we don't even need that much. Why don't we do this? Why don't we just take a quarter of the circle, rotate that around the x-axis, and then double that answer? What do you think? That seem reasonable? Okay, so if we're going to do this, we need to come up with a way of representing this rectangle in here. So we need to know the upper function and the lower function. And remember, I like to do this, put a little arrow here showing the axis of rotation, showing my axis of rotation here, drawing my rectangle here, and then that blue curve on top. What's the curve on the bottom? 0, y equals 0. So we do have two functions. The top function is the blue function, which is the circle, and the bottom function is just the constant function y equals 0. But what is this function? What is the blue function? We need to figure out what this is, f of x. So what do you know about circles? Do you know the equation of a circle? See if this rings a bell. Somebody gives you a circle. Wow. Right? Centered at the origin. radius r, it has the equation x squared plus y squared equals r squared. That look familiar? Yes? Okay, and if you offset the circle, if you move it somewhere else, and you make the center hk instead of 0, 0, then the formula becomes x minus h squared plus y minus k squared equals r squared. Those are your general formulas for circles. So hopefully you remember seeing that at some point. We are going to use this one because we're going to center our circle at the origin. Now, if we want this to be a function of x, what are we going to have to do with this? Solve for y. Now, we know that circles are not functions, right? They fail the vertical line test, but we're only looking at the top right-hand corner of it. So when we solve for y here, you're going to see what's going to happen. Let me solve for y. I'll do it right here. Y squared equals r squared minus x squared, taking the x squared to the other side. And then what do? Square root. But when you take a square root on both sides, you always have to do plus or minus. So which one of these are we going to use, the plus or the minus? The plus, because we want our y values to be positive, right, not negative, so that's going to give us the top corner. So with that knowledge, I can come back up here and I can say, all right, well, this is just the square root of r squared minus x squared. And notice I'm leaving r as a little r. I'm leaving it arbitrary. I'm acting like it's a constant. I don't know what it is, but it is a constant, all right? And then our g function, which is the bottom one, g of x, we said was just the constant 0 function. It's always flat. So when we rotate this around the x-axis, we will be using this formula from last class. The volume will be pi integral from a to b of the top function squared minus the bottom function squared. Yes? dx. So let me write that down here. The volume, should I draw it or? I don't mind drawing it. We're going to get this, right, when we rotate that? That volume should be pi integral. Let's talk about a and b in a second. What the heck is this? And then the f function squared. What's our f function squared? That was that square root of r squared minus x squared, but then we're going to square it, minus the g function, which was 0, squared dx. Right? That's what we have. It's a good thing, too, because when you square the square root, it goes away. What about our limits of integration? Where are we integrating from here? So go back up here. What's the beginning of this here? 0. And where do we stop the integration? How far out? R. The radius, right? We don't know what it is, but that's where we would stop. So our integral is going to go from 0 to r. Make sense? Okay. So let me do this. Well, I think I can squeeze it in down here. This is pi integral 0 to little r of just r squared minus x squared dx. And now all we have to do is take the antiderivative of this. And these are two terms, right? So I can do term by term integration. What is the antiderivative of a constant squared? So that may as well just be a number, right? Like 10. What's the antiderivative of 10? 10x, right? So the antiderivative of r squared would be r squared x. So I'm going to put that here. Also notice I'm going to bring my pi with me. The pi that was out front. I'm getting r squared x. And then what's the antiderivative of x squared? 1/3 x cubed, right? That's our antiderivative. We're going to evaluate 0 and r. So let's plug in. I'm out of room here. I'm going to have to bring this with me to the next page. So let's plug in R first. And when we plug in R, which letter are we replacing here? The X, right? The R is still just a constant. So I'm going to replace all X's with R's now. I get pi R squared times R minus 1/3 R cubed, right? That's what I get when I plug in R. And then minus pi times R squared times 0 minus 1/3 times 0 cubed. That's all going to go away, isn't it? This whole thing is going to become a 0. 0 times pi is 0. So that's all gone. And all we're left with is pi times R cubed minus 1/3 R cubed. What's R cubed minus 1/3 R cubed? 2/3 R cubed. And then we have a pi out there. So 2/3 R cubed, I'll say 2/3 pi R cubed. That is the volume of that piece, rotated. Now, what did we say the volume of a sphere was? 4/3 pi R cubed, but that was half. Remember, we only did half of it. So if you double this answer, so if you take that and you multiply it times 2, then what you get is the whole sphere, right? Which would be 4/3 pi R cubed. So that just verifies what we already knew. In fact, that's probably the way that formula was determined. That's kind of cool, huh? How about the formula for a cone? What's the volume of a cone? One-third pi R squared times height, right? That's the volume of this. So you'd have to know the radius, and you'd have to know the height of the cone in order to determine its volume. Do you agree? How could we do that using this rotation thing? Any ideas? Let me give you a specific example and see if you could come up with a way to find the volume of this without the formula, of course. What if your radius here was 6 and the height of this thing was, I'll make the numbers nice, 8. Okay, so use a triangle and lay it sideways. Okay, so yeah, you could do that either way. You could do this, right? Rotate that around the x-axis. You've got a cone, don't you? Or you could have done it this way, with your triangle going the other way. It doesn't matter. If you rotate both of those, you're going to get the same volume, aren't you? But my question to you next would be, let's go with this one because that was the first approach. My question would be, how are you going to determine your functions? So if you have your little rectangle in here, I hope it's obvious that the g function is 0. But what's the f function on top? It's a line, right? X equals, or y equals mx plus b. Isn't that a line? And don't you know that the distance from here to here is 3? Because that's half of the, oh, sorry, 6, sorry. 6. Because that's the radius, right? And don't you know the distance from here to here? That's 8. Doesn't that mean that this is the point 8, 6 right here? And doesn't that mean that you also know another point on the line, which is the point 0, 0? And if you have 2 points on a line, can't you come up with the equation of the line? Yes. And once you come up with the equation of the line, you're there. This one wouldn't be too hard to do. This would be y equals, it's just the slope in front of x. So what's the slope? How do you get from one point to the next? You go up 6, to the right 8, rise over run. So up 6 over 8, 6 over 8 is 3/4 x. That is the line y equals 3/4 x. And then that's your f of x. Any questions? I don't want to finish this problem out. I'm just going to write the formula for what it would be. The volume of this would be pi integral, where would we go from? 0 to 8, right? 0 to 8. And then the top function squared. So what's our top function? 3/4 x. We square it, so that would be 9/16 x squared. And then minus the bottom function, which again would be what? Just 0 squared. So, and then dx. Would that be a relatively easy thing to integrate? Yeah. So equals dot, dot, dot. I won't finish that. But if you do this with more general cone, then you would replace this 8 with what? H. You would replace 6 with R, and then this would change, right? And you would have R's and H's in here, and then you do all the integration. And if I bet you, if you do it, you would come up with this. So, okay. Now, let's try something. Where's my notes? There they are. See if I had some examples in here that I wanted to do. How about this? Example. You know what? I was doing notes last time. I was trying to keep track. Let's see. Did I put a note on that? 722 is where we ended last time. Let's just say everything I've done here today, this example here, let's call this 723. Let's call the next one that I did here, even though I didn't finish it, 724. And the one that I'm about to do, let's call it 725. All right, so let's find the volume of solid generated by rotating the region. Tear it open, man. Go for it. No, tear it open. By rotating the region bounded by y equals 1/4 x squared and y equals 5 minus x squared about the x-axis. I'm writing out all these words for the problem because that's the way they're going to appear in a test. That's the way they appear in textbooks. There's no easy way to tell you what they want you to do, so you have to just write it out. Okay, find the volume of the solid generated by rotating the region bounded by these two graphs, these two curves about the x-axis. So where should we start? do you think we should start with here? Draw them out, right? Let's draw the region that we're going to try and rotate. Once we draw the region, then we can determine all the pieces of like where it starts and where it stops. Now this is where, you know, I would encourage you to use the $100 calculators that you have, if you do have them, to just aid you in graphing, all right? These aren't too bad when it comes to graphing. These are just parabolas. But you may as well get what you paid for, right? You can use a calculator, yes, but you, of course, have to show your work. So it's a guide only. 1/4 x squared looks like a parabola. I know that. And I know it opens up because 1/4 is positive in front of it. And there's no number being added to the outside, so it's not shifted up or down. So I know it looks something like that. It might be a little more narrow, who cares? 5 minus x squared is a parabola that opens down. And you could have written it this way, negative x squared plus 5. That's the same exact thing. And if I write it this way, then I think it's easier to see that it's just the parabola that opens down moved up 5. So it'll look like this. That hits up here at 5. We all okay with that? And the region bounded by them is this piece right here. Now we could ask for the area, couldn't we? That's not what the problem is asking. The problem wants you to take that region and rotate it around the x-axis. So I can get to the rotation right now if I want, or I can go try and figure out where these two graphs intersect, because I'm going to need that information too, right? I'm going to need to know where they hit each other, because that's going to be my limits of where I start and where I stop. Agreed? Yes? So what would you like to do first? I don't care. Start drawing the rotation thing or get the intercepts? Intersections. Intersections? Okay, let's find the intersections. Maybe we should label the curves. I'm going to label the blue one F because it's on top. I'm going to label the red one G. Make sure that I know which is which. Okay, and the intersection, how do we find the intersection of those two functions? Set them equal to each other, right? So I'm going to take 1/4 x squared, set it equal to 5 minus x squared. And then what kind of equation is that? Quadratic, right? Quadratic. I don't like the fraction, so I'm going to just multiply both sides of the equation by 4. I'm going to add 4x squared to both sides. And then divide by 5. And so I get x is what? Plus or minus 2, right? So that's where they hit each other, at an x value of -2, x value of +2. I feel good about that. Questions? We didn't need to factor, we didn't need quadratic formula, right? This is just straight up, pretty easy quadratic to solve. All right, let's now set up the rectangle. Just to make sure we understand, I'm going to have to do it below this. We have our rectangle sitting there. We have the lower curve, and we have the upper curve. And so what we are trying to do, and this is a little more detailed than we actually need, but I'm trying to lead us into where we're going here in a second. What we were most interested in was the distance, right? This distance from the outer edge of my rectangle to the axis of rotation. Hear what I'm saying? We're interested in the outer radius, right? The distance from this edge to my axis of rotation, which turns out to just be the f function, right? That's all it is. This is f. So this is the 5 minus x squared. And then what we did is we said, okay, we need to know the distance from the lower edge to the axis of rotation, which in this case just turns out to be g. So this distance right here is the 1/4 x squared. And then the formula says that what you do is you take pi, integral, and then you take that outer radius, which was the f functions, and you square it. You subtract the inner radius, which was the 1/4 x squared, and then subtract them and integrate. So can I set up the formula now? Yes. Well, remember that on the exam for this section and the next few sections, a lot of it's going to be setting up of the integral. So I'd like to see as much as I can to give you credit for, partial credit for. Like if you just like draw this, right? If you just draw this over here and that's it, and then you write down a formula and it's wrong, you get less than you would get if you drew this and then I could see, oh, look, they got these backwards or something. Okay, so volume would be what here? Pi. Integral -2 to 2. Okay, listen to the way I'm saying this again. What's that outer radius squared? Which it's the 5 minus x squared, but then squared. So that's like my outer radius. And then what was that inner radius? Because I'm going to subtract it. 1/4 x squared squared. And then dx. That is the formula. Okay? Now, could we do that one? How would you integrate that if you had to? Just square everything out, right? Square this, so do your little foiling there, and then square that, and then combine like terms, and then just do term by term integration. It's a polynomial. This should go pretty clean. Understand? Equals ... I leave that to you. That's what I would expect to see on the test. If I say set up only, this is what I want. You don't even have to multiply this out. In fact, I prefer it this way because then I can really see what you called the outer radius and the inner radius. These are pretty straightforward. I think, I hope you see it the same way. Let's throw a little twist to this, okay? Let's see how this can get a little more confusing. I'd like to try and do the same problem, but I'm going to change something here. I'm going to change where we're going to rotate. Okay, so 726. You could just, if you're doing this in your notes, you don't have to rewrite the whole problem. Just change to say now, now rotating about, not the x-axis, about y equals 8. So what does y equals 8 look like? What is y equals 8? It's a line, right? Vertical, horizontal line. So back here on this problem, right, we took that region and rotated it around the x-axis. What would that have looked like three-dimensionally? This can get a little bit challenging. What would that have looked like if I rotated this around the x-axis right here? It's hard to draw it. I mean, it's very difficult to draw something like that by hand, which is why I'm not going to try and do it because, even if I could do it well, it would probably, unless you're really good at that stuff, it would be There's a learning curve to it. So, but try and visualize what it would be. I mean, it almost looks like something like that, and then just right around the x-axis, right? Like this, come back. So how about this? My description of it is a donut without a full hole through it. It's just kind of pinched off in the middle. Is that what you see also? Yeah? Okay, so if you kind of see that, I'll try and get a drawing of it in a second if we can, or get the computer to draw it. This drawing looks different because, or this solid would look different because you're taking that same region, which was, I went too far. Draw a little smaller. Here, the other one was like this. You're taking that same region, but this time, instead of rotating it around the x-axis, you're rotating it around y equals 8. Y equals 8 is up here, which means your axis of rotation is this. You see the difference? I mean, the axis of rotation is moved up. If I take that yellow and I rotate around that y equals 8, is that the same volume as the one we just did? What does it look like? Is it still my donut? Kind of? Yes? What's the difference though? It's larger, and is it pinched off in the middle? It actually has a hole in it, doesn't it? That can't possibly have the same volume as the one we just did, right? Can't possibly. So the formula for this has to be different. We can't get the same result. So let's try something here. The same approach that we've been using, let's try and draw my rectangle. And then out to the side, I'm going to start drawing everything else. Here's my x-axis. Here's my rectangle. Here's my blue function on the top. Here's my red function on the bottom. And now notice I'm going to bring my axis of rotation in up here. Go with me? Now here's where things get critically important. What we need for the formula was what I was calling the outer radius and the inner radius, right? The outer radius and inner radius. It was a distance, wasn't it? It was the distance from the axis of rotation to the outer edge. So what you need to now kind of visualize is, imagine we're looking from the top down. All right, we're looking like a top view, and you're a person standing here, that's the top of your head, and you're looking out towards this thing, right, from here to here. This red edge is the one that's furthest away from you, isn't it? That's now your outer radius. And what we need to determine is, what is this distance from here to that bottom edge? So what is that distance? So, hold on. What is this entire distance? All the way from you to the x-axis? 8. Does that ever change? No, that never changes, right? This is always 8. But if I slide this rectangle to the left or to the right, do you agree that the red and the blue are going to change as I move from left to right? Yes? So somehow this red distance right here, or this red curve, is changing, which means that this distance changes as I move. So somehow this red distance is not static, it's not fixed. It is a function of x. But what is it? 8. It's this distance, take away how much? That little piece right there, right? This little piece right here is the red one. I should have done it in red, right? But this is g of x, isn't it? Which was which one? 1/4 x squared. Y'all see that? Distance from the x-axis to the red we know is 1/4 x squared. So the distance from the red all the way to my axis of rotation is the 8, take away that little piece. So I need to write that down in here. This is going to be 8 take away the 1/4 x squared. Are there any questions? How about same thing, observer looking out to the inner radius, which is the distance from the axis of rotation to that closest edge. What is it? This time it's 8. Take away what? The blue function, right? The f of x. What's f of x? 5 minus x squared. So make sure you put it in parentheses, 5 minus x squared. And that, remember, is because from here all the way to here is 5 minus x squared. Do you see why the geometry of this and the drawing of it is so important? I mean, if you can get your head around what's happening here, all it is just plugging into the formula. It's just your outer and inner radius you have to be sure of. So in recap, this one right here is what I'm going to be calling my outer radius. And then this one over here is my inner radius. Once I have those, and I have my limits of integration, I'm ready for the formula. So the volume of this will be pi integral, still negative 2 to 2, because we found that in the previous problem, and then outer radius squared, so outer radius squared minus inner radius squared dx. What do we have? Just plug them in, right? 8 minus 1/4 x squared, and then 8 minus 5 minus x squared, but then all of that squared. And this would be a polynomial again. You would just expand everything out, get a result. Okay. Mm-hmm. Yes. This is the volume. This is the volume, not an area. So of this yellow thing, taken off the page and rotated around that dotted line. Yes. Volume, yes. Uh-huh. So that's what we call like a vertical shift, or we can do a vertical or a horizontal. You could just move this whole picture down, right? How can you move this whole picture down? Make this go down to here, right? Which would mean take this function and move it down 8. Take this function and move it down 8. Yes? That's what you're referring to? Yes, you could. I like that approach. The only reason I stay away from it is because I'm trying to get you to see something a little more subtle here, which is the formulation of the formula on your own, which works good whenever we do what are going to be perpendicular cross sections in a little while, where it's not as simple as just moving it. You have to actually understand where the formula is going to come from. And I think this kind of gets you thinking that way. So yes, you could have got the same result. And you might ask me, then, wouldn't it have been this one? Because you would just subtracted 8 from each function, right? So it would have been this minus this, right? And this would have been positive. And so they're not the same. But when you square them, it doesn't matter. So it turns out to give you the same result. Okay. Same problem, different axis of rotation. So I'm going to give you the same one. This time, I want it to go around y equals -3. if you want to use that method on the test, I wouldn't take off for that, if that's something you're more comfortable with. All right, I'm going to draw my same two functions. This. Where is my axis of rotation this time? It's below the x-axis, y equals -3, which is, I'm just going to exaggerate it down here. We're rotating around here, -3. Going to draw my rectangle. I'm going to come out to the side, make sure I represent my x-axis, my axis of rotation. Here's my rectangle. I have the blue on top, the red on bottom. We okay with that? All right. Your observer now is standing on the axis of rotation, looking out towards this rectangle and trying to find the outer radius. The outer radius is this distance, all the way from there, all the way down to here. And it is a distance, okay? It's a distance, like a measuring tape, you mark it out, right? So how far away is that blue piece? Let me ask you this. How far is it, that blue piece, from here? That's the x-axis, right? So how far is it from the x-axis to the blue? 5 minus x squared. It's just a function, isn't it? So this is 5 minus x squared, for sure. And what is this distance? Distance, 3. Isn't it? I realize it's -3, but distance-wise, measured out, that length is 3. So what would the total distance be then? Plus 3, add them together, right? So that total distance from here all the way is 5 minus x squared plus 3, which is 8 minus x squared. Do y'all see where that comes from? Using the same idea, what's the distance from, or the inner radius, which is from the bottom edge all the way down to the observer? It would be this distance from here to here, which was 1/4 x squared, and then plus 3 again. 1/4 x squared plus 3. Does this make sense? And so you have the outer, you have the inner, you set up the formula, you're done. All right, so the volume would be pi integral -2 to 2, outer squared minus inner squared dx. The outer here was the blue one, right? I'm going to go ahead and put them together. 5 plus 3 was 8. So this is just 8 minus x squared. And then the inner one was 1/4 x squared plus 3. And whatever that is the volume. Questions? I think I was supposed to change this to 726, right? Or was it, or were we on 7 now? Should have, this one was 726. Yeah, next one should have been 727. All right. Now, we need to throw a little bit more mess into this, all right? 7 to 8. What if we want to do something like this? Let's take the region bounded by y equals 1/4 x squared and y equals 5 minus x squared x equals 0 and x equals 2. And rotate that about the y-axis. Well, we haven't done that yet, right? We've gone around the x-axis. The x-axis is a horizontal line, isn't it? We've rotated around a horizontal line. We actually did y equals 8, which is another horizontal line. We did y equals -3, which is a different horizontal line. We have not done a vertical line yet, have we? No? Okay, so let's draw a quick picture. We've drawn this so many times now. Hopefully, we can just sketch it real quick. And also notice I'm only going to draw the right side of it. Why am I only drawing the right side? I said it's bounded by all of these. This, and this. So x equals 0 is a vertical line. X equals 2 is this line over here. So it's cutting that left side out. Do y'all see that in the wording? Okay. That's important because if I didn't cut the left side out, imagine rotating that around the y-axis. It would almost give you a double volume because it would go around it through itself twice. So just this piece around the y-axis. So my axis of rotation I'm going to illustrate here is this. Do you see a problem? Do you see an issue? Not terrible issue, but do you see some things we're going to run into? Yeah, we need to change these from being functions of x to functions of y, because we would need to have our rectangle go this way, wouldn't we? So that we could get our little disc or washer. Do y'all see that? Which means that we have to turn our heads and do it like we did with the areas. But there's got to be a more efficient way. And there is. And it's a different approach. It's this what we've done so far was what we call the washer or disc method. I'm going to now introduce you to a new method called the method of shells. And the method of shells is set up for this. It's perfect for a situation just like this. See, we are very comfortable with the rectangle being this way, right? That we're okay with because we have an obvious function on top and a function on bottom. They're both functions of x. The problem is we're trying to rotate it the other way. So do you remember when I said method of shells? I said this in class last time in your notes. Or not method of shells, method of washers. Where is it? Hold on, I need to silence my phone. Did I not put in here? I thought I put in here that your rectangle is always perpendicular to your axis of rotation. I said it. I don't think I wrote it down, did I? I don't see it anywhere. Just remember this right here, this method. If you go back up, we'll put it right next to the formula so you have it. Right here. Just remember that your rectangles is perpendicular. What's another word for perpendicular? It's more mathematical. You all heard this? Orthogonal? Well, now you have. Orthogonal is another word from perpendicular. Rectangle is orthogonal to axis of rotation. That's when you use this method. So everything we've done today, right? Everything we've done so far, on all of our pictures, when we rotated, this rectangle was perpendicular to the axis of rotation. This one, right? Perpendicular, here's our axis of rotation, it's perpendicular to it. For this, we have a question mark because the rectangle that we're comfortable using here is actually parallel to the axis of rotation. Do you see that? When this happens, you can use what's called shells. So we're going to stop here, and I'm going to introduce the idea of shells. 728, 729, method of shells. I'm going to have to draw a picture. What's key in this problem is to realize that you still have a region that's bounded by two functions of x. So you have like f of x, g of x. And that region, you want it rotated around not a horizontal line, but a vertical line this time, right? We're about to do it on the y-axis, aren't we? So let's see if we can come up with a formula or something for this. Here's the y-axis. I'm going to rotate around there. Here's my rectangle that I'm going to rotate. Does anyone remember me telling you in class to always remember that when you place a rectangle arbitrarily inside this region, that the distance from here to the rectangle is what? Anyone remember what I told you it was? We know the width of the rectangle is what? Dx. But the actual distance from the origin to our rectangle is what? Anyone remembers? Okay, if you know, it's just x. It's just x. It's some arbitrary value. And that x lives between what? A and B, the two endpoints of our region. So this is an arbitrary x. I want you to put that in here this time because we're about to need it. What would you get? Tell me, like geometrically explain to me what that rectangle wrapped around the y-axis would look like. Like what? What kind of pipe? Like bong or something? Okay. Giving you a hard time, Robert. It looks like this. Do you agree or not? Take that little sliver right here, bring it out of the page and back around through the back side and come back. Wouldn't it look like this? I'm getting looks of, it's hollow, right? Like I could put something through here down and pass it through because there was a distance between the axis of rotation and my rectangle. So when I wrap this around, I'm going to have this hollow space in between. That's very different than wrapping it around the x-axis. What did we say it looked like if we wrapped around the x-axis? Just so we can compare and contrast these. It would look like the washer, didn't it? It was like this, but it was hollowed out. Right? That's what happens if I rotate it around the x-axis. This is what happens if I rotate it around the y-axis. See the differences? Now, we came up with the formula for the volume of this, didn't we? Turned out to be pi f of x squared minus g of x squared. And we did it using the formula for a cylinder to do it. This one's going to be different. I know it looks like a cylinder, but how do we find its volume? This is where things can get a little weird. So I think in an effort to kind of save time, because we lost an entire day, what I want you to imagine doing, and we're trying to find the volume of that, right? I want you to come up here with a pair of imaginary scissors and just cut it open, okay? And lay it out flat. If we do that, it'll look like this. Yes or no? Yes? So it's now like a stick of gum, right? Laying down. So I would like to know the volume of this. And so it looks like a box, a parallel, we'll call it parallel pipette. It's a box, shoebox, a real weird shaped shoebox, but it's just length times width times height, right? That's all it is. The volume, length times width times height. So do you know, let's take care of the parts that are easy. Do you know the height of this? Do you know how tall that is? That's f of x minus g of x, isn't it? That is the distance from here to here, which is just the top function f minus the bottom function g, right? This is just f of x minus g of x. Do you know the little tiny little width right there? Or not width, whatever we want to call that. We'll call it width. Do you know that width? That's your dx, isn't it? Look, remember this came from rotating this little sliver. This sliver had a width to it. The width was dx. The only thing left to resolve is the length. So how long is it? You have a cylinder thing like this, piece of paper curled. You cut it, you lay it out. How long is it? It's the circumference, isn't it? The circumference of that circle laid out is how long it is. Do you know the circumference of this circle? Well, you need to know its radius, don't you? Right? What's its radius? That distance. Do you see that? That's the critical part. That's why we needed the x. The distance from here to here is your radius of this cylinder. So that's what gives you the radius for the circumference. So what was it for circumference? 2 pi r? So this will be 2 pi times my radius, but what's my radius? X. So the volume of that little piece, right, just that little piece, would be what? 2 pi x times f of x minus g of x dx. This times this times this. That's the volume of that little sliver. So how do I find the volume of the entire region rotated around there? Add them up. How do we add them up? Infinitely many of them? Integral. Right? So this is actually going to become our formula. So the volume of this will be, anything I can pull out that are constants in this formula? 2 pi. Integral. Now we're still going to go a to b. Okay, still going a to b. But the things that stay in here are x, because x is not a variable. I mean, sorry, is not a constant. And then f of x minus g of x. And then dx. And that is the formula for the method of shelves. Keeping in mind that your rectangles in this method, rectangles are parallel to axis of rotation. The rectangle that you draw is parallel to the axis of rotation. That's going to influence you. That's going to tell you, look, you need to use this one. All right, that's where the formula comes from. Now let's see if we can apply it to this problem. Go back up here, see if we can get this now. If we were to start the whole thing over, you draw out your region, you say, hey, look, I've got a function on top, function on bottom, very clear which is which. I've got limits of integration that go from 0 to 2. I'm happy. I want to leave my rectangle vertical. I would really like to. I'm rotating around the y-axis, which is parallel, right? Understand the parallel part of this? My rectangle is parallel to the axis of rotation. So I'm going to have to use shells. If you want, you could draw out your axis of rotation over here, kind of like we've been doing. You could draw your rectangle. You could draw your function on bottom, function on top. You can measure out your distance from here to here being x. And then you do your little rotation. What is the volume? 2 pi integral where to where? 0 to 2 of, let's see, what's next? X, that's just going to be there because that's our radius. And then parentheses, f of x, what's f of x for us? Careful, other way. It's the 5 minus x squared. I don't need to square it, do I? Right? And then I subtract from that what? The g of x, which is the 1/4 x squared dx. And that's it. You're done. That's your formula. You could collect like terms and combine and any questions? To start to give you an idea of what your test problem is going to look like, I'm going to give you a region. It'll be critical that that region is drawn correctly, that you have complete control of that region, that there's no question in your mind about what it looks like. Because the questions that will follow will be rotated around the x-axis. Rotate around y equals 8, y equals -3. Now rotate around the y-axis. Now, I'm going to give you like 5, 6 different rotations to do on one region. If you mess the region up, they're all off, okay? So just kind of get that on the back burner, that with the test coming up, every single region pretty much I give you is going to have to rotate around multiple things. And that shows a complete understanding of how the formula changes depending on where it's being rotated. All right, we're gonna throw another twist into this. Who said we had to rotate around the y-axis? The y-axis is just a vertical line, isn't it? That's all the y-axis is a vertical line. So why not just pick some other vertical line? Why does it have to be the y-axis? So how about a vertical line like x equals, we'll start with -4. So we're going to do the same region in the first quadrant, but this time we're going around x equals -4. That's a vertical line that's to the left of it, right? So here comes my drawing. I'm sorry? Oh, is this 10? Was the last one 9? Did I not change it? Oh, there it was. Okay, the shells was, sorry. We've got the little parabola thing here going up. We've got the parabola coming down. We've got a little region in here. We've got a rectangle in there. And our axis of rotation is over here at -4. Give you a second to draw that out. What's today? 7. Yeah, officially our exam is not going to be Thursday. We can't. That's what it says here. We don't have enough information yet to have an exam on Thursday. So I'm thinking maybe Tuesday, but let's just see how things go today. All right, so your rectangle that you like is perpendicular or parallel to our axis of rotation. Parallel. So we're thinking shells, right? So when we do shells, we need to make sure we're very, very clear on where everything lives. Because our formula is, it's not just a plug-in formula and you're done. We're going to do it just like we did with that, I said the observer sitting there and looking out, and you have to kind of account for things. Same thing here. Does dx change? Does the width of the rectangle change? No. Does the height of the rectangle change? Here and here. Does that change when I wrap it? No? What's the only thing that's changing this time compared to the other one? The axis of rotation is moved, right? Which means that when I rotate this, this is a little wider than the other one was, isn't it? What was the importance here? With this one, didn't we say, look, from the axis of rotation to my rectangle was x. That was the radius, right? The radius that we used in that formula right here. That x right there came from the circumference. That came from the distance from here to here. That came from this. What's different in this one is that our actual radius is not x. Do you see the difference? X is just from here to here. See, that's my y-axis right here. I need to add something to that. I need to add this distance. And what's that distance? 4. And we don't use -4 because it's a distance. So now you're, instead, in that formula, instead of using x here, we're going to use what? X plus 4 in parentheses, because it's a total distance. So maybe now's a good time to do this. This x is a little misleading, isn't it, in the formula? That's actually not always going to be x, is it? What's that always going to be? How do we want to say what that is so that we go back and we understand? I mean, what is it? It's the distance from the axis of rotation to our rectangle, right? This is actually the distance. I'll write it like that. It's the distance from axis of rotation to the rectangle. I like to just call it the radius. It's the radius, right? It's the radius of that shell. We'll call it radius of shell. This was called a shell right here. So once you know the radius of the shell, you just go to your formula. So the volume of this entire thing will be, because we're using shells, 2 pi, integral 0 to 2, radius of the shell, which I'm going to call, you could do x plus 4 or 4 plus x, doesn't matter. And then in parentheses, the top function, f minus x squared, minus the bottom function, which was 1/4 x squared, dx. And that's it, whatever that is. Multiply it all out, collect like terms, whatever. What do you think I'm going to do for the next example? X equals, yes. I'm going to put this axis of rotation on the other side, and I'm going to see how that changes things. So let's do our last one here for this. All right. Let's make this one, let's rotate it around 10. X equals 10. Has anyone noticed that I've kept the axis of rotation away from being inside the region? That's intentional. Because if you put your axis of rotation inside the region that you're rotating, it causes an issue. So we don't address it. All right, drawing. This time we're going out x equals 10, so here's my region. Getting tired of drawing this region. Axis of rotation is out here at 10. Yes. I don't know why I keep doing that. I just keep copying and then forgetting to change it. Yes, thank you. I'm going to blow this up over here so I can see it. Take out all that other crap. There's just my rectangle. Got the blue guy on top. Got the red guy on the bottom. Axis of rotation's out here. Is dx going to change? No. Is the top and bottom change? Everything's the same. The only thing that's different is the rotation. The rotation, the radius, is going to be distance from your axis of rotation to your rectangle. So I want to know what this distance right here is. 10 minus x. Because you know this distance from here to here is x. You know the distance the entire way, oops, too far, is 10, right? So this is just 10 take away x. Since you were asking, is it Gatlin? On the other one, it was a vertical shift, just moving things around. Have you seen this with a horizontal shift or something more like, you don't remember? Okay. All right. So we are interested in this right here, right? 10 minus x. That's our radius. Remember, our shell's going around like this, right? That's why it's our radius. It's going like that around. All right, volume, 2 pi, because we're using shells. 0 to 2, and then 10 minus x. Then the top function, 5 minus x squared, minus bottom function, 1/4 x squared, dx, whatever that is. I mean, do you see, imagine if I went and actually worked each of these out today. I mean, we'd still be back on, what, 7.25 probably. All right. Now, I don't want to sell you short, but because we lost that full day, which is the equivalent of 2 full lectures in a traditional semester, I'm just going to let you know that you can do this entire thing for functions of y also. So imagine you have something that looks like this. I won't test you on this, but imagine you have, this is, call this f of y, and then over here you call this, I'll make it intersect up there, call this g of y. You would not want to use vertical rectangles here, right? No? That wouldn't be a good thing because these are functions of y instead of x. So your ideal situation would be to use a rectangle that looks like that, right? So what if I want to go around the x-axis? What method would you use? Shelves. But everything is going to be in terms of y instead of x. What if I want to go around the y-axis? I'm going to use washers, but everything will be in terms of y instead of x. So everything can be switched over to handle situations where your regions look like that. But I'm not going to go into it. It's just going to be too much time. All right? So homework out of this section. Oh, wait, hold on. There's still one more thing we have to do. Sorry. Let me see if I can find this. I want to find this demonstration I have. There it is. I wish I could take that out of there. All right. It's hard to get that green thing out of there, but okay. Let's take a look at this. What I'm going to do here is first pose the problem for you. Let's say that we have, and what is this, 7-2-12? Okay. Volume of solid cross sections. All right, this is very different than everything we've just done. We are not, the idea here is not rotating anything around any axes, right? Just clear your mind of that right now, all right? Here's what we're going to do. We're going to take two graphs, and let's just go with the same ones that we just had. Like this. This time we won't restrict it to the first quadrant. Let's just take those two that we've been working with today. And imagine taking across, like just that infinitesimal rectangle right here, like that, this infinitesimal sliver, which I'm going to call a perpendicular cross section. So look, this little rectangle, this little sliver is perpendicular to the x-axis, isn't it? Okay. What I want you to imagine doing is taking that perpendicular cross-section and imagining that it is the base of a square. That little cross-section is the base of a square. So on the side over here, what I'd like to do is try and draw this in three-dimensional space. Here's the blue. Here's the red. Do you see it kind of laying down flat on a sheet of paper? Here's that greenish looking sliver. And I'm not going to give it any width, okay, just to make it a little easier to draw. Imagine that's the base of a square. Then do you agree if it's square, then it has to go up by the same amount, over by the same amount, and down by the same amount? Yes? Imagine that every cross-section perpendicular to the x-axis forms a square. So imagine taking the one back here. Do y'all see it? I'm going to highlight it. That one over there. Do you see that little cross-section over there? Over here in this picture, it would be somewhere around here, wouldn't it? Right there? And it would be a square, but notice that it's smaller, right? Because it's got a smaller base than the one I drew before. So it would look like a little square like this. Do you all see that? Imagine taking every possible cross-section and making squares out of all of them. Wouldn't that eventually form a solid here? Yes? What's the volume of that? So going back to this picture that I had for the demonstration, this is it right here. Can you see that one square? The first one I drew is like this one, and then the next one I drew is this one, or the one way back there. If I drew another one, it would be here. Do you see that this is the object you would get? It's kind of a weird shaped thing, right? But we can find the volume of that. That's what I'm saying. We can. We'll see. Got it? All right. So let's go back and try and find this. Let me pose the problem the way it would be posed in the book. The base of a solid S for solid, the base of a solid S is the region bounded by y equals 5 minus x squared and y equals 1/4 x squared. So we're sticking with those same parabolas. Cross sections perpendicular or orthogonal to the x-axis are squares. Find the volume. Perpendicular. So do you understand it? From the wording, do you understand what's happening here? These two graphs form the bottom of the solid. And then when you take a cross-section that's perpendicular to the x-axis, so if you start taking these cross-sections, they form squares. All of them together should give you a solid. What's its volume? So here we go. This is how you would do it. Draw your quick picture. Draw a typical slice. This time I'm going to give it some width. Lay that slice out over here on the ground. And just make a square out of it. Now it's not exactly a square because it has, it has some width to it, right? This would actually be a box, a parallel pipette. So the volume of that little sliver, isn't it length times width times height? Yes? Just that one little sliver. So you need to know its length. You need to know distance from here to here. Do you know that length? What is it? F of x minus g of x. Because that's really just the height of that rectangle to start, right? I mean, that from here to here, that's the f minus g. We've been doing that over and over and over. But since this is a square, this is also f minus g, because it's a square. And then the only thing left is the little width. But what's the width? Dx. So what's the volume of that one little sliver? F of x minus g of x, all of it squared. Not squaring each one individually. All of it squared times dx. That gives you the volume of that one little sliver, and we want all of them, don't we? So how do we get all of them? Add them all up, right? Integral. So the volume will be no pi or anything like that, right? Our formula doesn't have pi in it. It's just integral a to b. In this case, we'll know what that is. F of x minus g of x squared dx. That's it. So let's fill the blanks in because we actually know all this stuff. What's a and b for us here? -2 to +2. What's f of x? 5 minus x squared. What's g of x? So I'm subtracting it. 1/4 x squared. And then all of that quantity squared dx. Whatever that is the volume of that solid. Questions? For some reason, this always gets people on the test. Was it? Did I have it clicked on rectangles? Oh, rectangles, squares. These look like squares. They're all the same height. I clicked the wrong one. Look. I wish you would have said that earlier. This is a square. And then as you move out this way, they get bigger, right? Bigger. So this was actually what we were doing. But who says it has to be squares? Right? What about semicircles? Where each cross section is a semicircle. Or triangles. Right? Each one of these is different. So I let you pick. Which one would you like to see? Circles or triangles next? Triangles? Okay. We'll do triangles. It's hard. It's the harder of the two. Well, yeah, it is. So this will be our last example, then we'll take our break. I'm going to do the same exact setup here. The base of a solid is the region bounded by the same two curves we've been messing with. Cross sections perpendicular to the x-axis are what kind of triangles? Equilateral? Let's make them equilateral. That'll make life a lot easier. Oops. What do you mean? No, I would stick to equilateral or isosceles, which means I would just do a quick little, you know, refreshing of what those are. Equilateral means they're all the same, all sides are the same, right? All right, so picture perpendicular to the x-axis, this here. Lay it down. Let me just lay a line down first, then I'll add width to it in a second. I want an equilateral triangle out of this, right? Has a little bit of width to it, so something like that. Do you know the length of the sides? What's the length of that side? F of x minus g of x again, right? All the sides are the same. So it was easy when it was a square, right? Because it was just length, it was just whatever, side times side, and then we had the width. Here we have the width, right? Still dx. But what is the area of this face of this rectangle? Maybe we should look at it like this, just from the front. You know this side is, I'm just going to write f of x minus g of x, right? What's the area of a triangle with all sides the same? So there's usually two formulas for areas of triangles. One of them is 1/2 base times height. The problem with the 1/2 base times height formula is that you don't know what the height is. I mean, you could get it, but it would take a little work, right? What's the other formula? Anyone remember the other formula? This is such a useful formula to have. That's right. There was a formula that says if you have a triangle, it does not even have to be equilateral. It says if you know two sides of a triangle and you know the angle in between those two sides, then the area of this triangle is 1/2 AB sine of theta. And that theta needs to be, or this needs to be in radian mode if you're going to do it on a calculator, but it doesn't matter for us in this problem. The reason why that is useful to us is because we know two of the sides, don't we? In fact, we know all three. But if you look at these two sides right here, in order to find the area, all we would need now is the angle between this. But it's equilateral, which means all the angles are the same, right? And they all have to add up to be 180, which means they each have to be 60, right? Degrees, which means each one of these is pi over 3. So according to that formula, the area of that little piece will be 1/2 a times b. So that what? Squared times sine of pi over 3. What's sine of pi over 3? Pre-cal. Sine of pi over 3. Root 3 over 2. Root 3 over 2. So I'm going to bring the root 3 over 2, which is a constant. I'm just going to bring it out here, and it's going to turn this into what? Root 3 over 4 f of x minus g of x squared. So that's the area of that little piece. To get the volume of this little piece up here, we just need to add the little dx to it, right? All right, so the volume of this whole thing will be the integral from -2 to 2 of root 3 over 4, which I could have pulled out, but I'm not going to, f minus g squared dx. F for us was 5 minus x squared. G was 1/4 x squared. Whatever that is. Do y'all have any questions over this setup? Yes. Equilateral triangle, all sides are the same, means all angles are the same. There's 3 angles in a triangle. They have to add up to be 180 degrees. So each one of them is 60 degrees. Pi over 3 is 60 degrees. We're clear? What would be the difference if I said that these were semicircles? I'm not going to go through it, but let me just show you. Here's our rectangle on the ground. Semicircle would be like this, wouldn't it? Well, not like that. But you would need to know the area of that, right? And don't you know the entire distance across, which is the diameter? So you have to come up with a formula for that area of that face if you know the diameter. It's half of a circle. Okay. All right, let's take a break. Let's say we'll come back in about 10 minutes or so. Okay, I just sent you an email. I just sent you an email of homework. I called it, homework. And what it is it's the exam 2 that I gave this past fall. But the thing that's, I guess, most critical for you to look at right now tonight would be number 5. Let the region, let R be the region bounded by these curves with x greater than or equal to 0. Find the volume of the solid generated by revolving R about the x-axis, then the y-axis, and then same region around x equals 5, then around x equals -4, and then the same region rotated about y equals 10, and then y equals -3. So you can see it's 6 different rotations to do with one region. So that's just a good practice problem, or a good, I guess, view of what you'll see on the test. And then there's a base of a solid. Find the volume of the solid if perpendicular cross sections form squares. So I gave this picture, and they had to come up with the solid, the volume of the solid. All right. Okay, so this is the old test. I would just go through that whole thing, and then I'll provide the answers at some other point. I emailed that to you through Canvas. All right. 7.4. Now 7.3 was shells, but I included that in 7.2. Just kind of like squeezed it in there. 7.4 arc length. All right, up to this point, what we've seen with applications of integration is that we can get areas between curves. We can do rotations around the x-axis, y-axis, different lines, perpendicular cross-sections. We can find volumes. Now, sort of different idea, which is the idea of arc length. And you would think that this would be easier to do than what we've done, but it turns out it's a little bit more challenging. So let's say you're given a curve, just a single curve on some interval AB, and you want to find its arc length. That means if you were to come up here, let me see what I can use for this maybe. Don't have any cables lying around anywhere. No one. Who has the string? Didn't you have, someone had string last time? No string? Okay, well, I won't be able to do it. Imagine taking this, off the page and just, and imagine it was flexible and just straightening it out and then measuring how long it was, right? That's arc length. So we want to know if we straighten this out over here, it would have a length L. I want to know how long it would be. So here's the way we're going to do it. We have to come up with a formula. The whole idea of drawing the rectangles is gone because we're not talking about an area now, right? So let's imagine taking this little piece right here and zooming in on it, okay, on that little piece of arc. Now, on that little piece of arc, those two little red points would be like, somewhere in here, these two little red points. If I draw a right triangle like this, right? That's definitely not a right triangle because that blue part's curved, yes? So if I approximated it with a right triangle, the length of this hypotenuse is approximately the length of that blue curve, right? I'm off a little bit. But if I go into the infinitesimal, meaning I zoom in and zoom in and zoom in and zoom in, and make this little magnification get into the little tiny, just like it's the same concept of going to infinitesimally small rectangles. If we go to an infinitesimally small triangle here, then the error between these becomes negligible and it goes away. So what I really want to do is approximate the blue with the hypotenuse of this triangle. Now, this right here has always been our what? The length widthwise here has always been our delta x, our change in x, right? If you're going to go from this red point to this red point, this is our change in x. But in the infinitesimal, the change in x is called what? dx. And here would be what? The change in y, right? Change in y. So the length of that hypotenuse there would be what? According to the Pythagorean identity, this, I'll call it little l so we don't confuse it with the big L, which is the whole thing, would be the square root of dx. Let's do it this way. I think this will be a little easier. dx, let's call this dx dx, dy dx. This is how much x changes with respect to x. This is how much y changes with respect to x. So over here, dx dx squared plus dy dx squared. this thing dx dx, it's important to understand what we're saying is, what is the rate at which x changes with respect to itself? So if I change x by 1/1,000,000th, the change in the x with respect to itself is always 1. The ratio is always 1. All right, let's see if we can clean this up a little bit. What is this? 1 plus dy dx squared. What's dy dx? Isn't that just y prime? Yes. So if this curve is given by some function y equals f of x, then the length of this little blue piece is going to be the square root of 1 plus the derivative of y squared. Will be this length. And we want to add them up forever. So if we want to add them up forever, we need an integral. This is a very loose interpretation of what's going on, but you can kind of see where the formula is coming from. So capital L, that's the length of the whole thing, will be the integral from a to b of all of these little guys added up. You can do y prime in here. You can do f prime of x. Doesn't matter. Now, we need a differential, though. We need with respect to what variable here. So with all integrals, we have to have our integration variable, so dx. And that's pretty much it. So this is our formula for arc length. So let's do an example. This was, we'll call this 742. Next page. Find length of, now these problems have to be chosen very carefully for them to work out. So I want to give you one that gives you somewhat of a challenge. Yeah, that one's good. Of y equals 1 over x on the interval 1, 2. So draw a quick picture. Y equals 1 over x. I hope we all know looks like this. There's another side to it, but I'm not going to draw it. And we're only interested in the length from 1 to 2, which means this little section. How long is that section? Is the question. Understand? And all we're going to do is apply the formula. So what do we need in the formula? What are we going to need? The derivative. So we just take a derivative quickly. The derivative of this is negative 1 over x squared. Yeah? And then don't we need to square that derivative? Yes? In the formula, so I like to just do that here, square it now. I squared it 1 over x to the 4th. So the length of this little segment here will be the integral from where to where? 1 to 2 of the square root of 1 plus 1 over x to the 4th dx. Okay. Then, yeah, you get to go ahead and figure that out, right? How do we integrate that? Trig sub may work, but trig sub worked when we had like 1 plus, and then this was just like x squared or something. This is 1 over x to the 4th. So how about maybe just a little bit of algebra first? Why don't we find a common denominator between those? What would happen if we got a common denominator? Oops. You get that? Yes? Then what? What else could we do? We could maybe split it up like this. Like do the square root top and bottom. But I don't see anything obvious here. So what I'm trying to illustrate with this, let's bring up Wolfram. Let's see what Wolfram does with this. What was it? Integrate square root of, was it 1 plus 1 over x to the 4th? I'm putting it in the original form. Let's just see. What? Right, that's it right there? The antiderivative. Oh, the antiderivative is just what? This, and then what's capital F of I, hyperbolic sine inverse of that, and then E. Oh, the F is the elliptic integral of the first kind with parameter m equals. What in the world are they talking about, right? So, in other words, this is not an easily integrable function. They're using these weird functions you've never seen before. So the moral, again, of the story is when it comes to arc length, it's a very simple formula. But what you can actually integrate is usually very limited. And so when we pick a problem for someone to do on a test, it's got to be perfectly picked so that the algebra works out, or else something like this is going to happen. So here we stop. I would not give you something like that on the test and expect you to integrate it. So since I'm promising you on the test you will be able to integrate it, you need to be prepared for the algebra that's going to be involved. So now let me give you an example of one that can be worked out so you can appreciate the sort of algebra you're going to see, okay? Okay, this is a pretty classic one here. Find length of y equals x to the, no, that one's, yeah, that should work out. Let's see if this works out. Oh, I better be safe here. I was going to modify one of their problems, but it has to be picked so nice for it to work that I don't want to go into a danger zone here. I don't want to live dangerous. We could spend 30 minutes on something that we can't get an answer to. All right, there we go. Find the length of this curve. X cubed over 3, 1 over 4x. Y equals x cubed over 3 plus 1 over 4x. I just want to take a look at it. Where was it being graphed from? Or from where to where? 1 to 2? So it's this graph right here between 1 and 2. So it's a little piece of it right in here. We're trying to find its length. All right? So what do we need for this? I'm not even going to draw it. What do we need for it? Derivative. What's derivative here? Is that just x squared minus 1 over 4x squared? All right, just look at this right here as 1/4 times x to the negative 1, and then do your power rule. Negative 1 comes out, then subtract 1, and that's just this. Questions? What am I supposed to do with this? Square it. So that means x squared minus 1 over 4x squared times itself, x squared minus 1 over 4x squared. And then go ahead and expand this out. You should get x to the 4th minus, anyone? Anyone? What's this times this? What's x squared times negative 1 over 4x squared? Negative 1 over 4, right? Negative 1/4. And then when you do the inner one, don't you get the same thing? And then the outer ones plus 1 over 16 x to the 4th. So x to the 4th minus 1/2 plus 1 over 16 x to the 4th. That's your derivative squared. Any questions? Now, the length, right? The length of this curve is the integral from 1 to 2 of the square root of 1 plus that derivative squared, which we just found was x to the 4th minus 1/2 plus 1 over 16 x to the 4th. All of that dx. We can put the 1 and the 1/2 together. Or 1 minus 1/2. So we get 1/2 plus x to the 4th plus 1 over 16 x to the 4th. Now you cannot integrate these term by term. You cannot, because they're all trapped under a root. You can't just square the integral because that's totally illegal. Changes the entire problem if you square it. We're kind of stuck. So what we're going to do is get a common denominator between all of these down here, all of these in here. So look at that as x to the 4th over 1. Common denominator. Go ahead, no. The formula says that the arc length is the integral of the square root of 1 plus y prime squared. Here's y prime squared, right? and 1 plus that. Yes? That's everything in red is the y prime squared, which we found up here. So what is the common denominator I need here? What is a common denominator? 16x to the fourth, right? So this one I need to turn into a 16x to the fourth, so I have to multiply times 8x to the fourth on the bottom and the top. So here's where we are. Got 8x to the fourth over 16x to the fourth plus, what is this one missing? On the whole thing, right? 16x to the fourth, so I have to do 16x to the fourth on top and bottom, turns it into 16x to the eighth on top over 16x to the fourth. This looks like it's getting worse, doesn't it? It's actually going to work out great, though, which is why, again, this problem was hand-picked to work correctly. Since they all have the same denominator, I can combine them together, and watch what I'm going to do on top. I'm just going to put it in descending order. And then my denominator is 16x to the fourth dx. Anybody recognize anything here? This is a perfect square trinomial. It's 16x to the eighth plus 8x to the fourth plus 1 is something times itself. What is it, though? How about 4x to the fourth plus 1 squared? Isn't that what this is? Right? What's 4x to the fourth times itself? 16x to the eighth. Then you would do the foiling and you would get back this. You have to recognize that. But I'm telling you, expect it, you know, so. And then on the bottom, hey, can you write the bottom as something squared? How about 4x squared? Squared. You could, right? And since these are both under the root, can't you just take the squareds away from both of them? That's the whole point, is that it works out where the square root on the outside is going to wind up going away. You have 4x to the fourth plus 1 on top. On bottom, all you have is 4x squared dx, and then what can you do with this? Split it up, right? You could do this over this, and then 1 over this. It's just a polynomial, and then you integrate and you're done. I think the biggest issue with this problem is realizing that when you're at this point up here, you put everything together, common denominator, and then realizing you've got a perfect square in here. You need that to happen for the square root to go away. Questions? Okay. So that's it. I'm just going to give you, one example for arc length. Work on the one on the test that I sent out to you. I just want to make sure it's not the same problem. Where is it? It's similar. Look, this is pretty close to the same thing. See? So the algebra should work out pretty similar to that. So you might ask yourself, like, finding the length of a curve is actually pretty useful. You might be asking yourself, like, well, if it's so hard to get the arc length, then why is it useful? If we can't integrate it, then why is it useful? But the answer to that is that the things we can't integrate easily can be approximated using power series, which is coming up in Chapter 8. So we can get as close to a numerical answer as we want to get using other methods. We're just not at that point yet. First example I can think of that comes to mind is if I'm building utility poles and I'm hanging wires between the poles. We talked earlier in the semester about these being catenaries, which is a certain type of curve, right? Well, if I'm putting these here and I want to know how much, wire I'm going to be using for the entire, 20-mile run, I need to know the length of each of those, don't I? So measuring out using arc length formula on this, but that would be a very difficult integration to do because this function doesn't behave well in that formula, but we could approximate it using the power series. Okay. So now that we've got the idea of arc length, I want to revisit it real quick because I was not impressed with my own explanation of the formula. So I want to go back to it real quick. This little picture right here, I kind of want to redo this to convince you, because if I were you, I would be kind of skeptical as to why I just said and put a dx out there, because that's kind of what I told you, right? Just like throw a dx out there because it's with respect to x. I don't really care for that explanation, so let me try and convince you otherwise. I know most of you are just like, well, the formula, I have the formula, I'm happy, right? That's okay, but I want you to be critical of the explanation. Let's go back to this idea, that this is the change in x, the infinitesimal change in x, this is the infinitesimal change in y, and by Pythagorean, we have this. Remember, that's the way I started, and then I changed my mind? Do we agree with that? Yes? Now, over here I'm going to write something down. If you have a function of x over here, right? Function of x, then which we'll call y, then the derivative of that is dy dx. Yes? Do you agree with this? Now, if I solve this for dy, then I have this. F prime of x dx equals dy. So the differential dy is equal to f prime of x times the differential of x. And what I'm going to do is I'm going to replace that dy right there with this differential. And just watch what happens. You have square root dx squared plus f prime of x dx squared, which is dx squared plus dx squared times f prime of x squared. So all I did here was since this is multiplication, I just squared each one. I put the dx out in front. Notice these both have dx squareds in them. So I can factor out a dx squared from both of these. And since it's squared, I can take it out of the square root, can't I? So it comes out as a dx. And what's left inside? 1 plus f prime x squared. But f prime of x is y prime. And there's your dx. So that's where it comes from. That's a little bit, I'm happier. I can live with that. The math gods are happier if I explain it that way. All right. All right, next concept and last concept. I can't believe this is going to be the last concept for 7.4, or for chapter 7, is surface area. So this is actually not something that's always covered in this class, in a class like this, but I'm going to because it's a very simple formula. So imagine now that we have again a picture where we have this curve. And we know how to do a lot of things with this curve right now. We could find the area underneath it, couldn't we? From it down to the x-axis. We could rotate that around the x-axis and we could get a solid, couldn't we? We could take it off the page, straighten it out, and get the arc length. Theoretically, we could do all that. Now what I'd like to do is, I'd like to take that blue curve, I'd like to rotate it around the x-axis. It's going to create a solid, right? I want the surface area of the outside of that solid. Surface area, not volume. Totally different quantity. All right, I get it. So imagine again blowing this thing up. Right, taking that little piece. We know how to approximate that length, don't we? How long that is? We approximate it with arc length, don't we? If I take just this little sliver and I wrap just that little sliver around the x-axis, it would draw something like this. That's not good. I thought you were laughing at my drawing. Not doing good here. There. So this little piece is that little piece there. That is not solid, right? This is a rubber band. Okay? Looks more like a rubber band. I want to know the area of this rubber band. The area of it. So come in here with your pair of scissors and snip it and lay it out flat. If we take that and snip it and lay it out flat, it'll look like a big, almost like a rectangle, won't it? That yellow piece is this yellow piece here. Do we know how long this rubber band is? Think about it again. It's going to be the circumference, right? The circumference of this thing, because we opened it up. The circumference, to get that, we need the radius. The radius is distance from the x-axis to this edge, right? Isn't that the function's height? So this would be 2 pi times f of x. F of x is the distance from here to here. And then we need to know how long it is right here. And how long is that? And be careful because it's not dx. It's the length of this arc, isn't it? And what's the formula for the length of that arc? Square root 1 plus y prime squared dx. So the area of this parallelogram looking thing is 2 pi times the function times the square root of 1 plus the derivative of the function squared dx. Add them up. Pardon? And then the integral is going to add them all up. And that'll be the surface area of the whole thing. All right. So what we get for the surface area, again, if you just like formulas, integral a to b. Now there's a 2 pi in the formula that can come out. F of x, I'm going to say instead of f of x, y, because y is the function of x. 1 plus y prime squared dx. Doesn't this look a lot like the arc length formula? The only difference between this one and the arc length formula are those two pieces. You take those two pieces out, you're back to arc length. You put those two pieces in, you're now talking surface area. I'm scared to do it, but I think we're going to do it. What's the surface area of a sphere? According to your notes or formula sheets. 752. Area of a sphere is supposed to be what? 4 pi r squared? Is that what you said? Yes? That's what the formula is, right? Those were on the... Oh, I'm not going to... Never mind. I'm not going to go there. Let's verify that formula. So what did we do to verify the formula for the volume of a sphere? We took that quarter of the circle, right, and we rotated it around, and we found the volume, and we doubled it, and we were like, okay, yeah, that matches. We should be able to do the same thing here, except take that quarter and wrap it and get surface area instead. So let's just revisit what that was. It was this piece right here, right? We had already said that that was y equals the square root of r squared minus x squared. We were going to go from 0 to r. So I've got my function. If I'm going to find the surface area, I'm going to need to find its derivative and square that derivative, right? Okay, so help me out. What's the derivative of this? So you need some chain rule here. Remember, r is a constant. Isn't the derivative of the square root of something 1 over 2 times the square root of that something? Times the derivative of what's inside. What's the derivative of what's inside? Remember, r is a constant. So just minus 2x. Clean it up. Do y'all understand that I'm taking the derivative because I realize my surface area formula needs the derivative in it, right? It needs it squared. So there's my derivative. Can I square it now? My derivative squared is, oh, that's nice. Negative goes away. And the root goes away. Yes. This is looking, oh yeah, it's looking doable right now, for sure. Okay, here we go. Surface area should be, according to the formula, 2 pi integral, what's my limit of integration here? 0 to r of, now be careful, what's first? Y. Y was the function itself, right? Square root of r squared minus x squared times what? Square root of 1 plus x squared over r squared minus x squared. Hold on, now this is starting to look bad. We all good? What did we do before under this root to try and make things be better? Common denominator. Let's do a common denominator between these two. I'm going to do it on the side because I don't want to rewrite the whole thing. What would that common denominator look like here? We'd have to do r squared minus x squared over r squared minus x squared plus x squared over r squared minus x squared. So I'm rewriting the 1 as this. And then when I combine these together, man, things are going to be real nice. Don't the x squareds up top cancel? And so you just get r squared over r squared minus x squared. So this is just this, right? And I can split this into 2, can't I? Because it's a fraction. And what's the square root of the top? R, and the square root of the bottom is just, well, the square root of the bottom. So this whole thing right here, everything in this root is going to turn into this. And that is going to be a great thing. Yeah, everything cancels out except what, r? Root r squared minus x squared times r over root r squared minus x squared dx. The roots cancel, and you have the integral of a constant. Nice. What is the antiderivative of r with respect to x? Rx. So this is 2 pi Rx, and we're evaluating at 0 and R. So plug in R for X, and what do you get? 2 pi R squared. Plug in 0, you get nothing. So this is the answer. But that was half of it. Double that answer, 4 pi R squared. Understand? Y'all don't look impressed. It's okay. Maybe I'm the only one who gets excited about this stuff. It's all right. I mean, you know, these formulas, they don't just, no one handed them to us, right? I mean, no one was like, here you go, I know you're going to be trying to put men on the moon someday. Here's some formulas that you might need, right? This is all us coming up with this. So it's nice when you can see where they actually come from. I think it's nice. All right. That should be a real good review. That exam I gave you, that should be a real good assignment for you to go home and try and knock out for homework. I'm trying to decide here where we need to trim, where we need to kind of pick up. There's a section 7.6 on applications to physics and engineering that I would like to try and push to the end of the class, only because we can live without it. I mean, one thing that you have to remember in a calculus class is that I know a lot of you are engineering majors, computer science majors, but really math is a very general subject. And then when you get into like physics or chemistry, then you pull the math that you need into that. And so this section on applications ranges from finding centers of mass to hydrostatic pressure to finding the work done. I mean, there's so many different things. My hope is that when you get to that in another class, you realize that the math part of it that you need to know is how to integrate, how to set up the integral, how to evaluate the integral. But how it's applied to something, that can be pretty, there's a lot of different topics. I will give you one just general example of it without getting into too much detail. In Cal 1, I hope that you remember that if you were given a distance versus time function, that if you took the derivative, f prime, here's f, that the derivative would give you the instantaneous velocity. Remember that? Someone gives you where something is at every point in time, the derivative gave you instantaneous velocity. In Cal 2, we don't really mess with the derivative. We're talking about antiderivative, and we found out that there was a connection between a function and the area underneath it. So how could that be used in something, something useful? So one example is distance and force. So if you have a distance versus force curve, you could say distance or displacement if you want that. Then what would this area underneath represent? Think about what the infinitesimal is. This little rectangle, this area right here, gives you the multiplication of these two quantities. This is an infinitesimal width, which is an infinitesimal what? Displacement times what? A force. What's force times displacement? Work. Physics. This is physics. Work is force times displacement. So if you take a displacement force curve and you were able to integrate it, find the area underneath, that would give you the total work done over the entire period of time, or through the displacement. So, I mean, that's just one sort of application. You could do this with any quantities. If you do time here and you do speed here, or velocity, and you find the area under the whole thing, again, go back to the infinitesimal. What is this? Well, this is time, right? And this is speed. If you multiply time times speed, what can you get out of this? What is it? Distance. Right? If you travel for 2 hours at 30 miles per hour, that's going to give you the distance you travel, right? So by multiplying these two together, you get the distance. So if you add them all up, then you now know what your displacement was, what your distance traveled was. It's very different than in Cal 1. Cal 1, we're talking about tangent lines, and that's instantaneous rates of change. Areas under curves gives you the product of these two quantities, and it adds them up. Now, if these two quantities mean something, then it means something physically. Does that make sense? I hope so. All right. What time did we get out? 12:30? Okay. We're going to start Chapter 8. When do y'all want to do a test? I mean, your options are Thursday or Tuesday. Tuesday? Tuesday? Okay. So Tuesday, it would cover everything I do through today. All right? That way, your next test will have the heavy stuff on sequences in series. But I'm going to start sequences in series today. So you'll get a little bit of this on this test, which will take place a week from today. Okay? So you're going to have improper integrals, areas between curves, volumes, you know, everything that's on the syllabus, but including 8.1. Well, scratch 7.6. So 7.6 won't be on the next test. So 7.6, going off the syllabus, scratch 7.6 or the schedule, but include 8.1. Well, yeah, I mean, here, you can look at it. My battery's about to die, so let me change this out. Okay. Trying to get my notes up for this here. Has anyone looked to see if there are notes for Chapter 8? No? All right. I'm going to try and motivate today with something that'll kind of get your juices maybe flowing a little bit. I'm not sure if it's possible, but what is this whole thing with series about? Sequences and series. This is Chapter 8. So here's what it turns out at the end of the day to be, all right? I'm going to show you it graphically. There's many things you can do with sequences and series, but the one I want to show you, I think, will make the most sense visually for you. Power series, here we go. Where is e to the x? Log. This one will work. I'm waiting for my computer to catch up because it's got to think for a second. Come on. It's not responding. Technology is great, isn't it? I think I brought my computer to its knees. Okay. Try it again. I won't scroll so fast this time. All right. If I asked you right now to integrate this function, could you do it? Yes, that's just going to be a natural log, right? That would be a very simple function to integrate. So the need here for power series isn't as important because we could integrate that anyway. But the idea here can be illustrated pretty well of what the power series is going to allow us to do. So I'm going to act like I don't know how to integrate this, all right? I have no idea. And what I want to do is try and come up with a way of representing this function as something else, as a different function. And I'm going to try and guess right now. I'm going to use, this is the function I'm trying to use, which is the function 1/5. So I'm saying y equals 1/5. Y equals 1/5. Y equals 1/5 is a constant function. Do you see it right here? Is this black function a good representation of this red one? By the way, this is a vertical asymptote. Act like it's not there. The computer had a problem with it, so it just drew a vertical line. Is this black one a good representation of this red one? Yes or no? Not even close, right? I mean, it's just a flat line. Would you say that this one is any better? So what I've done is I've changed it from 1/5 to 1/5 minus x over 25. So isn't that just a line? This time it's not horizontal. I mean, not horizontal. It's got a little tilt to it. Is that a better approximation of this? How about this? Now I have a quadratic. Now, the dotted line behind that's still there is the one that I had previously, which was just that horizontal line. I would say that that quadratic's maybe a little better, but not that great. How about that cubic function? A little better? How about that 4th degree? A little better? 5th degree? 6th degree? 7th, 8th, 9th, 10th, 11th, 12th, 13, 14, 15. Am I getting better? Oh, man. I'm getting better, aren't I? And better, and better, and better, and better. And so what's happening here, and look in here. I'm like right on top of that thing. Like I would argue that in this little window, I would say that my approximation is pretty damn close to the true function, isn't it? This right here is a series. When you think of series, you think of like one thing following another. This is a series of powers of x, power functions, right? X squared is a power function. X cubed is a power function. X to the fourth is a power function. This is a series of power functions, and they approximate this function pretty damn well. It turns out that if you have a continuous function, which is one that you can draw without picking up your pencil, a continuous function, you can always approximate it with a power series. And you can approximate it as close as you desire. So you're building aircraft parts, you need to be within a certain tolerance. I can come up with a power series to represent that function as close as you need my tolerance to be, the tolerance to be. I can go, it means I have to go out pretty far, but I could do it. And the beauty of it is that if I want to integrate this or differentiate this, I don't have to look at this, I just look at this. Could you integrate this? Term by term, right? What's the antiderivative of 1/5? 1/5 x. What's the antiderivative of negative x over 25? Negative x squared over 50, right? This integration of each of these term by term would be simple to do. It would take a long time, but it's not like an impossible integration. Understand? So you can represent these functions with these power series. There's another one. This one's kind of cool to see. So I'm approximating this one, the red one with the black one, and it's not good. It's better. It's getting better, better. Where'd it go? The computer's doing a lot of work right now. So, see? The computer can handle this. It's just having trouble graphing it all and everything at the same time. Yeah. I've just brought it to its knees. So before we can actually get to that and see the things that we're going to do with it, we just need to know, what the heck is a sequence, then a series, and then there's certain behaviors that we have to be careful with series. They have these things called radius of convergence, where they behave well, and then outside of that interval, they don't behave well. So, but to build up to that, we have to start with the most basic idea, and that's what a sequence is. So when someone says sequence to you, what do you think? What's that? Pattern, okay, like a sequence of numbers, right? So a sequence is a list of, in this class, numbers. But I'll say could be anything. Right? You could have a sequence of dogs. Right? There's a dog, different dog, different dog. I mean, doesn't matter what it is. And here we're going to start by looking at sequences as a list of numbers. And let's look at some examples. This may seem very, like a very elementary idea, but it's important that we all have our head around it. When we represent a sequence, we like to use a set of braces. 1, 2, 3, let's say all the way out to 100. That's an example of a sequence of numbers, right? This would be considered to be a finite sequence. Finite because what? It stops, right? Finite. Here's another sequence. 1, 2, 3. This time, I don't want it to stop. So what I do when I don't want it to stop is I say dot, 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 and then I put the other brace there. This is your infinite sequence. So your sequences can be infinite or finite, right? So in general, when you're looking at a sequence, you have like a first piece, then a second piece, then a third piece. So what we do is we like to write it this way: A1, A sub 1, A sub 2, A sub 3, and that may stop or it may not stop, right? Let me do one that stops first. A sub K. This is a finite sequence. How many elements are in this sequence here? K of them, right? But if you have this, the 3 dots implies that it goes forever, which means that this will be infinitely many elements in that sequence. Here's another sequence. What is implied by that? What is the pattern that you see in that? It's just evens, right? Starting with 2, 2, 4, 6. That's what we think it is, and I would agree that's probably what we mean by that, right? 2, 4, 6, 8, 10, forever. You could do the odds. Doesn't matter where you start either, right? I mean, a sequence is just a sequence. So what we're going to be interested now in doing is seeing if we can come up with a formula that generates the sequence. So can we find formulas that generate a sequence? A sequence is just a function. But the domain is the positive integers. So what do I mean by this? Let me take you back a little bit. If I defined a function right now, f of x, to be equal to x squared, the idea from algebra and everything else is that you can plug any number you want into this, right, and square it. So you could plug in 1, you could plug in 2, you could plug in pi, you could plug in square root of 2, you could plug in anything, right? There's no restriction. So when you graph it, it's a nice, smooth, continuous parabola, right? That's your traditional function. What I'm saying here is a sequence is a function, but the domain is restricted to the positive integers. So it looks more like this. It's a function. I'm going to put n in here, n squared, where n is a positive integer. So to compare these two. What is the difference between f of x equals x squared, where x is allowed to be anything, versus f of n equals n squared, where n is a positive integer? What is the difference graphically? They're dots. Where does it start? 1, 1, you have a dot. You don't have anything else, right? Then you plug in 2, you get what? 4, right? Then you're allowed to plug in what? 3, and you get 9. But it's not a continuous function, is it? It's a function that just spits out a bunch of dots. And that's because the input is restricted to just numbers. Now, how can we see this relationship back up here with these sequences? Well, I only did, what, a couple of them right here? These and this one. How can we rewrite, how can you write these sequences as functions? These 3. Let's try it. So write 1, 2, all the way out to 100 as a function. So generate that list with a function. What would the function be? Just n, right? The function would be n. F of n is n. So you plug in 1, you get 1. You plug in 2, you get 2. You plug in 3, you get 3. But you need to be able to stop it. So how do you tell me, how do I tell you to stop it? And what? Positive, right? Positive integer less than or equal to 100. And this becomes a pain in the ass, doesn't it, to write it this way? So instead, we have a different way of doing it, all right, which is what I'm trying to illustrate here. Because it's a sequence, everyone needs to know we're restricted to the positive integers. So we'll write it like this instead. Forget this notation completely, and we write a sub n equals n. So we're replacing this functional notation with subscript notation. A is the standard letter we use for a sequence. Subscripting is like the n in here. So it's saying what you're going to do is you're going to replace that n right here and plug it into this formula, right? N is going to be n. And with sequences, we are going to always start at 1 and go until you want me to stop, right? So I want to create this sequence, n less than or equal to 100. That's all I have to say. It's implied that n is going to start at 1. And it's going to stop when it gets to 100. So what's a sub 1? 1. What's a sub 2? 2, right? A sub 3. 3. And do you see how there's a match? The first element in the sequence is 1. The second element in the sequence is 2. The third element in the sequence is 3. Yes? Okay. That's how we would create this right here. All right, how would you create this one? So what would this be? A sub n equals n again, right? The only difference is what? I don't stop it. And if I don't stop it, that's all I write. That's it. Again, it's implied n is a positive integer. Now, there are some alternative notations, but these are the ones that I'll use. An alternative notation, I'll write it in green next to this, is this. To put a brace around it, put n equals 1 to infinity. That's another notation for a sequence that you could see. These two things mean the same thing. You're going to start at 1. You're going to create this sequence with n starting at 1. It's going to go up 2, 3, 4, 5, and it's never going to stop. Up here, this notation would have been n, and then n equals 1 to what? 100, see? So these two are the same principle. Does this seem pretty straightforward? Okay, because I'm gonna start doing stuff now that some of you are gonna be like, what? And some of you will be like, yeah, I got it, it's easy. And I can't explain why it happens, it's the way people's brains work, all right? So let's see how long you can hold on to this. I want you to see if we can continue to write these as functions. Write 2, 4, 6, forever. Write that as a function. I'll give you a second, and then I'll ask for a volunteer. And I'm going to ask for volunteers the rest of the way, but I'm not going to let anyone answer more than once. So if you answer once, you can't answer again. Somebody give me the A sub n. Any volunteers? To n. To n. You have to always remember, what's the first n you're going to plug in? 1, right? So if I try a sub 1, it's 2 times 1, which is 2. Does that match up with the first one there? Yes. A sub 2 would be 2 times 2, which is 4. And does that match up with the second one up here? Yes. And so on and so forth, and it would generate the list. We good? All right. They're going to keep getting harder. I'm not saying that one was hard. I'm just saying they're going to get harder. Okay, same idea. These are almost kind of fun, I think, because it's like a puzzle. Whenever someone has it, you can raise your hand and, okay? 2n minus 10. So did you just realize these are all even numbers, except that you needed to shift backwards, start at a different number. So you're using this same formula, which you know spits out 2 initially. You needed it to spit out -8, so you subtracted 10 from it to get it to take you back to -8 to start. Then the next one should be 2 more than that, so -6, 2 more than that, right? So 2n is always going to count even numbers, right? And then this right here is just going to adjust where you are in the even numbers. Got it? Good. Next one. This isn't any harder, it's just make sure you're understanding it. Who's going to give me this one? Two n minus 2. Same idea, right? It's the even numbers shifted over 1. Now, I wanted to show you that one because these are the even numbers starting at 0, right? And the one that we did up here was the even numbers, where is it? Starting at 2. And those are pretty common. A lot of times you'll want to start off, you'll try and start a sequence off and you're like, I need to get the even numbers, but I want them to start at 0. So you'll use 2n minus 2. Or you'll say, I need to start at 2 instead, so you use the 2n by itself. So just be familiar with those. All right, I'm going to keep going here. Haven't talked about these yet. Don't want to leave them out. What is it? 2n minus 1. So these are the odds. Right? It's just every even number starting at 2, take 1 away from it. right? Every even number starting at 2, but then subtract 1 from each one, so you get all the odds. Good. How about if you wanted to start at 7? (2n plus 5). Good. All right. So I'm remembering who's answered here. Y'all are out. What I'm going to do is I'm going to eventually get down to the people who are shy. And we're going to get them up, stand them up, and embarrass them. Here we go. You may as well put a big asterisk next to this one now because this is majorly important. Who's up? You won't? -1 to the n. -1 to the n. Does that work? What's a sub 1? -1 to the first power. What's -1 to the first power? -1. What's a sub 2? -1 to the second power, which is, you square it this time, it's positive. And then the third, hey, this is going to work, right? -1. And the next one, because it's even, will be, right? That'll work. This is a, well, I start it because it's so important. This is how we make what's called an alternating sequence, a sequence that changes signs. You can use this -1 to the n. Now let's contrast that with this. What if instead I wanted to go 1 -1, 1 -1 instead? What's that? Who's someone? It's got to be someone new. It's not the same one, right? It's not the same sequence. So let me help out. With this one, the idea was that when we plugged in 1, we wanted it to be negative, right? So we just knew that we needed to leave it alone. Then when we plugged in 2, it was going to square and become positive. This is opposite. When we plug in 1, we want it to actually be what? An even number, so positive. Like the power, we want the power to be even, so it'll spit out a positive. Then when we plug in 2, we want it to be odd. You could put a negative sign outside. That's one way. You could add a 1 to the n. That's another way. They're the same thing. Watch, let's look at them both. One idea was, why don't we just put a -1, you don't need the 1, but in front of what we just had before, right? And that would make everything we had before change its sign, yes? The other proposition was to just take the -1 to the n, but this time add 1 to it, up here. I claim these are the exact same thing. Do you see it? What's -1 to the 1 times -1 to the n? Same base, add exponents. You get this, right? Check it though. Plug in 1. What happens here? 1 plus 1? 2. So you're squaring it. The first number you plug in 1, you're actually squaring it. And when you plug in 2, you're going to get 3, which is going to make it odd. You plug in 3. Yes. You could also do n minus 1. It wouldn't. That would be the same as dividing by -1. As long as you offset it by, you can't just, you could do, there's so many different variations. You could do this, n minus 1. You could do a to the n plus 3. Because if you plug in 1, what do you get? 4. Sorry, that was supposed to be -1 in there. -1. All of those will result in the same thing. But the one that is used most often is this one, right here. And over here, this one. So please make sure that you are aware of those two. One of these starts you out at the evens. This one starts you out, starts you out at negatives. This one starts you out at positives. And we keep going. How about this one? See if you can get it from that. If you haven't answered, you're free to volunteer. ⅓ plus 2n. Well, I don't know. We can try it. What would happen if you plug in 1? No? See, but you got to try, right? You got to do something. Okay, so I'll open it up to the class. Everyone now. Anyone have it? No? Okay, let me come over here. Does that help? Those are what the last two are. What is 1? What's another way you could write 1? 2 to the 0. And this is 2 to the -1. And this is 2 to the -2, isn't it? So a sub n is 2 to the n minus 3. Okay, hold on. The 2's the same in all of them, right? Same base all the time. And then aren't the exponents just going up by 1 each time? So this is like counting 1, 2, 3, 4, 5, 6, except you're starting where? At -2. So you have to shift it over. So we know that n by itself would just start counting 1, 2, 3, 4, 5, 6. But if we take away 3, then when we plug in 1, we get -2. When we plug in 2, we get -1. When we plug in 3, we get 0. And it creates the pattern. You see that? Now does everyone see it? Yes? So these can start to get kind of messy. We're not quite to messy yet, but now you've seen that. It's in your memory bank. All right, let's see what you do with this one. Sorry. Okay, I'm going to let you all work on that. And then after that one, I'll give you another one. Just do that one. Any of you there on this one? One or two? Okay. Okay, I think that's enough. Let's see if we can figure this out. So when I see things like this, I always look like, first, is it alternating? Is it positive, negative, positive, negative? Is it doing something like that? In this case, it is. So I know right away that I'm going to need to make this thing alternate, starting with positive, then negative. So to do that, I'm just going to put a -1 to the n plus 1 out here. If I do that, I'm guaranteed to start out with a positive term. Then my next one will be negative, then positive. So that eliminates me even focusing on the positive, negative part of this. Then what I like to do is I like to look at each one and see if I can kind of break them up as fractions and see if there's a pattern in the numerators and denominators. So like, look at the numerators. Forgetting the sign, the negative here. 7, 9, 11, 13. Those are all odds, right? Starting at 7. So how could I create that numerator? 2n plus 5. That would give me all the odds starting at 7. Then I look at the denominators. Is there a pattern here? 1, 3, 9, 27. They're all powers of 3. Starting at what? 3 to what power? 0. So when I plug in 1, I need to get 0. So 3 to the n minus 1. This will create that sequence. Now, please keep in mind, there's a possibility that you may get a different answer that is correct. So sequences do not have unique representations. As long as it generates the sequence, it's okay. All right? Now, some sequences you can't come up with a formula for, like this one, the famous one. I may have given it away already. How many of you have seen that sequence before, right? This is the Fibonacci. So there's no way to define it easily with a formula. And because of that, we have to have another way. And there's another way you can define sequences, and that's what's called with the recursive definition. So what's the pattern in the Fibonacci numbers? Someone who knows it, share it. Anyone know the pattern? Okay, so to figure out, you go out to one of the numbers here. This number is always going to be the sum of the previous two. So 8 is 3 plus 5. 13 is what? The previous two. So 13 is the previous two, 5 and 8 added together. So what would the next number be, right? 21 is 13 and 8. So what would the next one be? 34? Because that would be 21 plus 13. Yes? And then after 34, you can get the next one. See, but the problem with the recursive definition like this is in order to know what the next one is, you have to know the previous two. You can't just go out to the 100th term and tell me what it is right now. To do that, you have to come all the way back to here and eventually build out to it. Now, there are other ways, but there's no easy way. All right? So what's the definition? Here it is. Hey, but what about 1? There's no 2 in front of it, right? What about the first one? There's no 2 in front of it. No 2 to count. So that's what we mean by recursive. Here's the way it works. For a Fibonacci sequence, we define a sub 1 to equal a sub 2 to be equal to 1. That's the first thing. What we're saying with this is that the first two are 1, okay? Everyone got that? The first two terms are 1. Now, a sub n is equal to a sub n minus 1 plus a sub n minus 2 for n greater than or equal to 3. This is the definition of the Fibonacci sequence. You start out by defining the first two. And then this right here, let's translate this. Let's use an example. If n is 3, this is saying a sub 3, that means the third one here is what? A sub 3 minus 1 is 2, plus a sub 3 minus 2 is 1. It's the previous two added up. So that guy is these two added. And then, of course, you place that with 4. This becomes 3 and 2, and that's the previous two to that. Okay? It's Fibonacci. All right, I'm not going to get into the golden spiral. I'm going to let you all go, but you need some homework out of here. This is not the homework for the whole section because we're not even close to finishing that section. But this will be the part that's included on your exam. 5 through 8. It's only 4 problems. They just give you a sequence and you find the formula for it. That's all that is. All right, everyone. Yeah, sign-in sheet. Yeah, I'll get out of here. It's okay today.